most rocky planets because of Jupiter's change of orbit. A new generation of rocky planets has come into existence.
Planets of the solar system, it is my pleasure as your son to introduce our newest, fully formed, fully developed rocky planets. Now, if you would, please take a moment to introduce yourselves.
Hey everyone, my name is Mercury.
And mine's Venus.
Hello, planets and celestial bodies of the solar system. You may call me Thea. I'm absolutely thrilled to meet each and every one of you, whether you're a rocky planet, a gas planet, or even... Giant star! So, a little about me. My favorite hobbies are...
Anyways, I'm Earth, but you can call me Proto.
Excuse me, I wasn't finished.
Yeah, you were. The sun asked for our names, not your entire life story.
I don't even have a life story yet. I was just being polite. Do you have any idea how important first impressions are?
Oh, I do, and let me tell you, you're ruining yours.
Mars, Mars, yep.
Anyway, time to socialize. But please be very careful when moving around. I have big plans, and they definitely involve you guys not dying. Okay? Okay. Enjoy.
Why is everyone so big?
Maybe because you're so small.
Hey!
Come on, bro. I'm stating a fact.
Here's another fact. You're only like 2.5 times bigger than me, Venus. That doesn't put you in the big planets category. Are you even listening to me? Oh, I see. I see.
See what?
How you look at Thea.
What? Dude says I'm... What do you care anyways?
Want my honest opinion? She's way out of your orbit.
Don't listen to him, Venus. You got this. Hey, Thea. I don't know if you heard me earlier. I'm Venus.
Can you believe that, Planet? He just made me look bad in front of everyone!
Oh, Proto-Earth? Yeah, he's a jerk. I already don't like him.
Same! He should know his place. You know what, Venus? I think I'll give him a piece of my core.
Yeah. Not literally, though, right?
No way, dude, really?
Yeah, I swear I saw a tiny planet floating around in the asteroid belt.
Maybe it was an exoplanet.
Exo what?
Come on, Mars, we should totally check it out.
How about no?
Hey!
Oh, hey Thea, what's up?
Apologize to me, Proto.
For what?
For what? How about for ridiculing me in front of the entire solar system?
Oh, you mean... Okay, look. I know you don't want to hear this, but you were kinda already doing that to yourself.
Me? Oh, so I guess it's kinda my fault?
Yes, you were going on and on about yourself. I didn't want to wait until the end of the universe to get a turn. So, can we please move on?
No! Not until you say sorry.
And if I don't?
Then I guess we're not friends.
I guess we're not.
Fine!
Fine! Wow.
Yeah, they sound like an old married couple.
Yeah. Wait, what? Nothing. Nice meeting you, Venus. Well, what?
Are you gonna introduce yourself to the new rocky planets?
Good. Thanks.
Oh, come on, Jupiter! I don't want to leave my orbit, okay? Last time I did, well, you know what happened. I know, but these planets can keep themselves in their orbits. Come on, stop punishing yourself. Tell that to X.
Who's X?
Mars? Oh, I meant excuse me? Yeah.
So you were saying, tell that to excuse me? Weird sentence.
Yup, that's me. Weird Jupiter.
Anyway, I wanted to introduce you guys to everyone. They're all super intimidated by you.
By us? But we're so friendly.
And, 20 times bigger than most of them.
Mars, we would love to come.
Yay! All right, I'll lead the way.
Saturn, don't be rude, okay?
I'm sorry, Proto didn't apologize.
Come on, Venus. You're sorry because he's not sorry? Don't waste your sorriness on that fool.
Yeah.
Anyways, I wasn't thinking about Proto. There's something else troubling me.
Who's been troubling you? Is it Mercury? Oh, I'll teach that little...
Venus, just listen for a second.
Sorry.
The sun said he had big plans for us, then refused to explain. What was that all about?
I don't know. He's kind of weird, honestly.
Yeah, but still, he's the sun. So, hey, I've been thinking, what if we go?
Are you guys not coming?
Coming where?
The gas giants. Everyone's meeting them.
Oh, finally. Okay, let's go.
You two go ahead. I have, some things to think about.
Oh, do you want me to?
Venus, go have fun. Tell everyone I said hi.
Sure. Will do. Bye.
Come on, we're the new ones here. We want to know more about you.
Yeah. Why are you all so massive?
Wanna take this one, Jupes?
Me?
Well, in short,
Gas giants like us formed farther from the sun, where ice was more abundant. Early on, we built up these huge, icy cores which had enough gravity to pull in tons of hydrogen and helium.
Whoa.
That's so cool. Hey, you know everything, Jupiter.
well,
Hey guys, what are we talking about? The gas giants were sharing some awesome solar system fun facts. Wow, that's so cool. I'm Mercury, by the way. It's a pleasure, really. I just wanted to say it's a
Hey,
real
where's
honor to be
the,
amongst
where's
giants
the
like
lady?
you.
Oh, you mean Thea?
Yeah, she stayed behind?
Yep.
Did she say why?
Let me think. First, you ridicule her in front of everyone.
Hey, I didn't mean to.
Then you refuse to apologize to her. So, yeah, I wonder why she didn't want to come.
Fine.
What? But fine what?
I guess you have a point. I'll go now and apologize.
Wait, I wasn't telling you to go and...
So you don't want me to apologize?
Yes. I mean, no. I think you should. Of course. Go do that.
Okay, I will.
Then, get moving.
I am. Jeez.
wanna watch the next part? And
How to get unlimited money in Animal Company. We're not
Sponsored by Novium. 3 years ago, I set out on my most complicated mission yet. I bought one of the biggest legally available rocket motors, put it in a custom carbon fiber airframe with a supersonic guidance system, and I sent that thing to Mach 3 and 30,000 feet in the name of answering one searing question. Can you cook meat by going fast?
5, 4, 3, 2, 1. Ignition.
This is high stakes, pun intended. It's a rocket with a specially formed nose cone and a copper tip designed to cook a piece of meat. As it gets up to 3 times the speed of sound, the air around the copper tip compresses so hard that it gets super hot. We're gonna use that heat to cook a piece of raw steak and return it safely to the ground under parachutes. This project is the culmination of years of work with control systems, fluid dynamics, composites manufacturing, milling, turning, and routing. It's a culinary innovation. It's an ICBM, but the M stands for meat, and it better work, because whatever happens, we're eating it. The first problem to solve is getting anything to go Mach 3, but this is easier than you might think. An L-class rocket motor with some fins and a nose cone can get you to Mach 3 just fine. So what is an L-class rocket motor? Model rocket motors are classified by impulse, and with every increase in letter, the total impulse roughly doubles. An A motor is pretty small, an F motor is a little bigger, and I think you see where this is going. An L motor is about this size. With a few fins and a nose cone on top, this thing can get us up to Mach 3 to cook a piece of meat. But the problem is, we're not just carrying meat on this rocket. This thing needs to have cameras, flight computers, batteries, parachutes, and all those things have mass. So now we have a dilemma. The rocket is heavy, what do we do about it? There are basically 2 schools of thought here. The first is we could optimize the mass. We could remove the cameras, we could get rid of one of the flight computers, we could deploy a drogue parachute and forget the main. The other option... What do you think I'm going to choose? After L, we have M, which is double the power, and after M, we have N. This is a tube, you can see right through it. But it's about the size of an N-class rocket motor. Among the available N motors, one stands alone, delivering over 20,000 newton-seconds of impulse in just 3.5 seconds, and topping out at over 8,000 newtons of thrust. No motor has killed more rockets than the N5800. The N5800 is a beast of a motor and responsible for countless shredded rockets. Dumping 20,000 newton-seconds all at once means it's very hard to keep the rocket all in one piece due to extreme aerodynamic and structural loads. This motor is made by a company called CTI, and it is so insane that in 2009, when they released it, they created a competition to go alongside it. If you could set the altitude record using the N5800, CTI would give you 2 free motors, each valued at about $1,500, plus a free case and hardware. In the pursuit of that goal, many Rocketeers have sadly lost their rocket to this monster of a motor. So naturally, the biggest, baddest, meanest rocket-eating motor there is... that's the one I want to use. To keep this rocket in one piece, I'll use a carbon fiber airframe to keep things strong and lightweight. For the fins, I'll use carbon fiber too, but this stuff is going to be super thin. thick. That's because I'm hollowing out the inside of each fin to install servos and control surfaces inside. Steering rockets is something I've done for a decade on this YouTube channel, whether it's thrust vector control, reaction control systems, reaction wheels, or now movable fins. I have a lot more fun when the rockets I fly involve control systems. Plus, it makes the footage a lot more watchable when the rocket doesn't spin a bunch. Because of this, the fins end up being super thick to accommodate those servos, so we'll add huge epoxy fillets at the base to match. It may look like this rocket is overbuilt, but we must remember, we're flying with the N5800, and the N5800 got hands. To make sure high stakes doesn't become a statistic, I laid up several carbon fiber sheets around the upper section of the booster where the yaw pitch bending loads will be highest. This is also where the drogue parachute and avionics section will attach. All this information means is that this section of the rocket goes under a lot of stress during flight, so we need to make sure it doesn't fall apart. Everyone knows that a good coat of paint makes the rocket go faster, so after a base coat of white, I made a stencil out of paper with manual cutouts for each letter and gave the whole thing the name High Stakes. Getting a paint job right is worth spending time on. I allocated about 2 days in the launch prep process to making sure this thing looked good. The primary colors are red and white with black for the text, and I really liked the chevron idea on the fins, so I repeated that for the upper section. I think it's worth spending time on a paint job like this, even if it doesn't meaningfully impact the flight. Like, there's a legitimate argument that the glossy surface reduces drag and all that, but it's worth being proud of what you build, and it's a lot easier to be proud of something that's nice to look at. I spent valuable time on this paint job, and you can't argue it wasn't worth it. This thing looks sick. Anyway, we gotta wrap this section up. If you want to know more about this booster, holy Moses, it's your lucky day. I have a 42-minute video all about the build process right here. Before we continue, ever since I was a little boy, I've known what I want. And what I want is to tell you about the sponsor for today's video, Novium. Novium makes these incredible hover pens that hover in this mount, and you know what? Instead of doing this in front of a green screen, I should just put the footage behind me. The Novium Interstellar Hover Pen sits at a 23.5 degree angle, which is the exact angle of the Earth's tilt. Most importantly for a pen, the writing on this thing is beautifully smooth, and it comes in a variety of colors, so if what you're seeing on your screen doesn't float your boat, there are a ton of other options. And speaking of options, there are actually 2 pens that I want to tell you about today. The first is the Hover Pen Interstellar, which I've shown so far, and the second is the new Hover Pen Traverse. Novium just launched this Kickstarter for it, and just like the Hover Pen Interstellar, this floats in a beautiful magnetic mount. The craziest thing to me is that you can get the Apollo Limited Edition, and they'll put an actual piece of the gold foil from the command module from Apollo 11 in the pen. Hover pens use refillable ink, so when your ink runs out, you can replace that easily, and they make excellent gifts for anyone who's got an eye for detail. If you want to give the Hover Pen Traverse a shot, you can get 30% off by backing the project on Kickstarter. And for those who want to get their hands on a hover pen sooner, you can use the code BPS to get 10% off on the website, and all these links are in the description. Thanks so much to Novium for supporting my childhood dream of getting to tell you about the sponsor for today's video. And now, let's get back to it. Next up, we'll need some electronics to control these fin tabs. So this avionics section will go right above the booster and get a BPS Ava flight computer, a huge battery, a GPS, and a telemetry antenna. Ava will use the inertial measurement unit to track the yaw, pitch, and roll of the rocket, then generate control commands for the aft tabs. It's going to send those commands to the booster via a VGA cable. And if you're wondering, why would you use a VGA cable to do that? Oh my gosh, your day keeps getting luckier. I got a whole video about that right here. The short answer is that VGA allowed for a lot of redundancy in the connection between the avionics section and the booster, which is going to help because this is a very high stakes flight, so we don't want this thing to fail. It also allows for the two sections to separate at apogee, which is going to be necessary to get the drogue parachute out. Wow, this footage is so beautiful. I wonder how it was captured. I know how it was captured. It's these 4K 120 frames per second cameras that we put into the avionics section. These cameras got mounted pointing up, down, and out. I have a background as a videographer, so getting the highest possible quality footage matters a lot to me, so I spent a lot of time on these. The cameras are originally GoPro Hero 10s, but they overheat when you look at them the wrong way, so I added an aluminum block as a thermal heat sink to absorb a lot of the heat during flight. That extended the recording time from about 4 minutes to 45. I also added a new ribbon cable so the sensor can flex around a little bit more. And if you want to know more about this process, holy shit, you keep getting so lucky. I have a whole video about that right here. How do you keep getting so lucky? So, how do we know if the meat is going to cook at all? What if this thing goes up and down and the meat doesn't get hot enough? There's a real risk that I give myself food poisoning here, so we need to be sure about this. I mean, cooking the meat is mission critical. This is my friend Elliot. I'm not going to tell you where he works or what he does there, but Elliot is one of the most geeked up aerothermal engineers I know. Basically, his job is to determine how hot things get when they go fast. Elliot was looking for a side project, so I tossed him a CAD model and a flight profile, and I let him cook. This guy stinks! Yikes. While he's working on that, let's talk about the shape of the nose cone and, more importantly, the shape of the meat. In 2014, ex-KCD author Randall Munroe asked the bold question, from what height would you need to drop a steak for it to be cooked when it hit the ground? Randall found out that if you drop the steak from high enough, yes, it will cook, but it's going to char the outside while leaving the inside mostly raw. Inspired by this answer, Tom Fisher and Thomas Rees of the University of Manchester put a beefsteak into their wind tunnel at Mach 5 to determine about the same result. I want all of the meat I put on this rocket to cook, so what do we do about this? Well, according to a thin slice of meat needs no thermal transfer to cook the inside. We'll sear one edge with aerothermal heating, and the slice will be thin enough that the whole thing will reach a safe internal temperature. Now that we know the shape of the meat, let's talk about the shape of the nose cone. A sharp conical nose tip will optimize for the highest possible heating on the steak, but we don't want the highest possible heating. I'm a professional chef. I don't want to char the hell out of the meat. I want a beautifully seared meal. I want culinary excellence. I want a cut of meat that is so perfectly cooked that Gordon Ramsay himself has to take up high-powered rocketry in order to compete with me. Instead of that sharp conical shape, I'll round the tip off, and this also increases the amount of meat we can cook. Let me show you what this looks like using my CAD program OnShape. I'll make a small copper shell to protect the meat from getting blasted away by dynamic pressure in flight. This copper is thermally conductive, and the meat gets pushed up against it by these spikes I milled out. All of this will help us cook a higher quantity of meat. I don't want to just cook a tiny piece, I want enough for me and my friends to share. That way, if the meat doesn't cook, it's not just me, we all get food poisoning. It's called high stakes for a reason. The nose cone itself is custom made using a 3D printed mold, fiberglass sleeve, and XXL condoms. Fiberglass has a very low thermal conductivity, which means we don't need to worry about the heat transferring from the copper tip into the fiberglass. If you're wondering why I needed to roll XXL condoms down the tip of my meat rocket, they're a mold release. They help keep the fiberglass from bonding to the 3D print. What did you think? Oh, gross, dude! If you want to watch any of these videos, by the way, these are all in the description down below. I've been covering this for the last few months, and this is the last video in the series, so you should watch them after this. To get to the launch pad, a rocket must pass several milestones. First, we need to know the parachutes will deploy. So we do this by performing a pop test. High Stakes uses a dual SEP, dual deploy architecture. At apogee, the booster and avionics section will separate to deploy a 2-foot drogue parachute. This keeps descent rate fast so the rocket doesn't drift far, but it's too fast to safely touch down. So the second deployment is the main parachute in the upper section. This is a 72-inch iris chute that deploys a few hundred meters above ground to give the rocket a softer touchdown speed. If you want more detail on this testing and recovery system, you guessed it, there's a whole video about it right here. Next, let's make sure we can talk to the rocket. When it's on the launch pad and in the air, there are 4 separate RF channels to monitor the rocket. Each Ava flight computer works off powerful 900 MHz radios with encrypted links. This is how we'll monitor GPS location, meat temperature, and a ton of other metrics. We also have a less powerful 900 MHz link to a Fluctus flight computer and a 400 MHz link to a telemetrum. These 2 computers are in charge of additional tracking and parachutes. After verifying that each computer had a strong telemetry link and could achieve GPS lock, I ran a final batch of simulations and began prepping for flight, starting with motor assembly.
Hey, I'm the N5800 guy.
The N5800 is shipped in pieces with 6 grains of propellant that get glued into the liner. This is always a stressful process as the fits are tight, and if a grain gets stuck, the whole $1,500 motor is useless. Once the grains are in, the liner is loaded into the case, the nozzle is seated, and the case is closed off. This case is then loaded into the booster to complete the lower section of the rocket. I secured the motor at the aft with grub screws and tossed a layer of speed tape over them for good measure. After loading the main chute into the upper section and attaching the guidance package to it, the whole forward segment of the rocket is attached to the booster to complete pre-flight integration. Now there's one last step, the most critical part of all. On L-1, we set out in search of a payload. Coming in at $90 a pound, we selected high-grade A5 Wagyu beef. To keep things sterile, we boiled the copper nose tip and all utensils that came in contact with the meat. The night before the launch, a slice of meat was cut up and loaded into the copper nose tip, then placed inside a cooler. The cooler will be brought to the launch site to keep the meat chilled, and the tip will be installed 20 minutes before flight. Without a goal, you can't score. Let's define some success metrics. For the rocket itself, it's very simple. It needs to go up fast, come down slow, and land within walking distance.
Can someone start a timer on their phone, and that's going to represent when the first avionics powered on?
For the meat itself, the USDA specifies a minimum safe internal temperature of 63 degrees Celsius, so if we're going to eat it, it's gotta pass that number. God, what is this in Fahrenheit? Doesn't matter if it's imperial or metric, someone's gonna be mad. Is 145 degrees Fahrenheit. That's 336 Kelvin and 605 degrees Rankine.
Okay, next up is servos. We're looking for Y plus to Y minus, Z plus to Z minus.
The meat needs to get above 63 degrees Celsius, and for that reason, I installed a custom Ava board in the nose cone. This Ava has a telemetry antenna, a GPS radio, and 2 thermocouples that stick up into the meat to sense its temperature. Ava will monitor the temperature of the meat during flight and beam that data to the ground. As for predictions, Elliot, the geeked up aerothermal engineer from earlier, had finished simulations using an estimated flight profile. Using CFD software as well as some custom tools he developed, he came up with an estimated temperature curve for the meat. The sim estimates that most of the heating occurs while the rocket is supersonic, capping out at about 218 Fahrenheit or 103 Celsius. This gives us a wide margin above the USDA minimum safe temperature, but it won't get too hot and burn the meat. The USDA also specifies that once cooked, food must be consumed within 2 hours. Not only must the rocket work, not only must the meat cook, but once the rocket lands, we need to get to it and eat the meat within 2 hours. If it lands in the surrounding mountains, we're cooked. If we lose telemetry during flight, we're cooked. If we lose GPS coordinates, we're cooked. If anything bad happens and we can't find the rocket, it's going to be a really bad day for us and a great day for foodborne illness.
Man, this is a big rocket. All right,
vertical. All right, you ready, Charlie?
Yeah. We have telemetry.
3 beeps.
We have good battery, apogee, and main voltages.
Great. First, I'm gonna do the servos to make sure those are good. That's Y plus. And Z minus.
Onboard data logging is ready. No GPS satellites yet.
We got 4 satellites in 40 seconds. 5 sats. This all looks fine. All right, ground station time. The rocket is launching from the Friends of Amateur Rocketry test site in the Mojave Desert. For smaller rockets, it's easiest to film and monitor the flight from the site itself. But for larger rockets, getting further away can help maintain a visual track and improve the quality of telemetry during flight. You get a better angle when you aren't looking directly up at the rocket. We drove out to this location about a mile away to start setting up the ground station. It's here that we'll place laptops and antennas for telemetry, cameras for filming the flight, and it's where we'll run the live stream for the folks supporting this project on Patreon.
We're getting about 20% of packets.
But I'm only getting very intermittent telemetry, so we're not really connected. The downside of a remote ground station is that the telemetry signal needs to travel through a mile of brush between the ground station and the rocket, which are at the same elevation. Antennas can of course be raised up, which helps a bit.
Oh, all right, we got RSSI of -104.
Yikes.
But,
But at some point, a critical decision needs to be made.
if we know we have good telemetry, and we know we can launch,
I think it doesn't matter if we think we'll pick up better. I just think from a regular risk perspective, there's almost no chance that this is a problem with the actual telemetry. When the rocket lifts off, it'll clear the brush and it should be just fine. But as the rockets I build get bigger, the decisions I make need to get better. This is so annoying, but we've got to make good decisions. It is a big rocket, it is a dangerous rocket, and I'm not gonna launch with spotty telemetry. I've made that decision before, and it's almost always the wrong one. We made the tough call to relocate the ground station to about half the distance with a lot less brush interfering with the telemetry. Doing this ate up valuable time with the rocket idling and burning batteries on the pad, but the new ground station gave us much stronger telemetry, and with that, it's time to cook some meat. I don't feel good. I haven't felt good all day. I wish I was in like a good mood, and I think as soon as it lifts off, I'll be in a great mood. It does not matter if it shreds. It's been a real mess of troubleshooting all day, but I think it's happening. We're gonna have a really great debrief meeting, I can tell you that much. That thing has just been cooking on the pad all day long.
Copy that. We are getting good telemetry from all relevant sources. CT, DW, plus weight at -2011 seconds. We have confirmation it's a graphics issue. Over.
It's still cold in there. Ever since I was a little boy, I knew I wanted to cook a piece of meat by going Mach 3. It's been a dream of mine since I was this tall.
Yeah, Launch Director, this is Charlie at the away site. I'm thinking I would like a piece of Wagyu A5 cooked medium well, please. Over.
I feel it squish. Yeah, we can do that. It'll be to you in a couple of minutes. Can I get a yes, chef? Yes, chef. Oh! That is a long motor.
We have meat temperatures of 65, 68, and fluctuating along with watchdog timer results. Over.
All right, Adams, sanity check. Camera roll. That's rolling. Cool. All right, it's time. The last time I launched something this big, the drogue failed and the rocket was destroyed. I've learned a lot since Lumineer, and I've tried harder to get this one right. But there's only one way to find out if that effort was enough. I think we are ready. I think we've done all we can do, and thank you all for being here. Thank you for watching. All right, you guys ready?
I'm ready.
Go, chef. All right,
Call it in.
call it.
Bar, this is BPS away site. We are go. Over.
All right, we got a go. Lead rocket in 10, 9, 8, 7, 6, 5, 4, 3,
2, 1, fire. Holy shit. Holy shit.
7.5 kilometers. 8 kilometers.
8,300, 8,500.
8,500.
Says drogue. That's
minus
minus
41.
40.
Minus 45.
That's looking like a drogue.
Negative 40 meters per second. That's
I see it, I see it, I see it. Straight up, there's a little smoke trail.
Oh, yeah.
Oh, hell yeah.
It's flashing a little bit in the sun.
We have good telemetry on all computers. 6 kilometers, 6.5.
The drogue parachute deployed nominally, slowing the descent rate to about 40 meters per second. But something odd shows up when watching the down-looking camera. The upper section should still be attached, but as the rocket falls, it swings into view. The up-looking camera is slightly blurry from paint that's stripped off at supersonic speed, but it gives us a clearer image of what's going on. At drogue deployment, the shock loading on the Kevlar line was a little too intense, and the shear pins for the upper section were undersized, leading to a premature separation. Luckily, the main parachute is still packed tightly inside, but as we keep watching, it gets even stranger. A charge in the upper section fires shortly after apogee, attempting to deploy the main parachute. I set the deployment logic on one of the flight computers a little too conservatively, specifying that if the vehicle started falling faster than 60 meters a second, to deploy the main parachute. The noise in the barometric speed estimate just barely passed this threshold, and in a normal scenario this would have caused the main parachute to deploy at apogee, letting the rocket drift far away. But in a bizarre turn of events, two wrongs kind of made a right. Because the upper section had prematurely separated and the main charge happened to be in front of the parachute, it fired without consequence. High stakes continued tumbling down at 40 meters per second under the drogue parachute until about 1,000 meters when the main was finally yanked free.
Oh, there's the main! Wow, look at that!
This was only 500 meters above the planned main deployment altitude, and upon passing that, the backup main charge fired.
Oh, there's the second charge. I think the main came out early. Is it coming closer to us?
Yes, it is. It is drifting towards us at 3 meters a second. Beautiful.
Booyah. Wow. Wow.
So our marks are not as useful.
Oh my god.
Went so straight.
So good. That was so beautiful.
You think we cooked it?
I have no idea how hot the meat got. I'm hopeful that it cooked, but I'm not really convinced, so we'll see. Let's get coordinates if anyone needs coordinates.
With the flight complete and the clock ticking, we packed up the ground station and headed off into the desert. From telemetry and recorded data, we can start to get a sense for the flight. Reaching 8.5 kilometers with a max speed of Mach 2.6, the flight was a little lower and slower than initially planned. Which is a crazy thing to say, considering this 50-pound rocket pulled 32 Gs and went so fast the paint started falling off. But that's okay, because the meat reached 103 degrees Celsius, 217 Fahrenheit. Although the data is very noisy, the meat remained above the USDA minimum safe temperature for about 20 seconds, then cooled off through the remainder of the flight. When adjusted for initial temperature, this curve is remarkably close to what Elliot simulated earlier.
We're close. We're almost there. We're like 3/4 of the way there.
As for the guidance system, the roll, pitch, and yaw axis were relatively stable for the first 15 seconds of flight, both in sub- and supersonic regions. But about halfway up, an oscillation develops on the roll axis and then spreads to pitch and yaw. This comes down to assumptions I made in the modeling process that didn't match up so well with real life. But even with these oscillations, the pitch and yaw control were able to keep the rocket pointed to within less than a degree of vertical. This helped bring cross range on ascent to about 200 meters at apogee with a lateral velocity less than 2 meters per second, a whole lot better than the 45 meters per second experienced by Lumineer.
All right, we're close. Presumably there's a rocket out here.
The landing site ended up being a little under 1 mile away, which is not far for a rocket, but is a little inconvenient if all you're out there for is a tiny piece of meat.
Yeah, it always seems easy to spot on a drone, and it never really is. No one see anything? I'm worried we have the wrong coordinates. Or maybe a little bit this way? It's behind it, maybe? See if it's behind a bush? Yeah, maybe spread out a little bit. Oh, I got it!
The fins are actuated.
Wow! Look at this! That looks so cool.
This is awesome.
Meats for dinner.
Congrats, man!
Oh, this is awesome. This separated real nice.
The rocket landed in excellent shape. I mean, structurally, at least. Mach 2.6 was not kind on the paint.
The rail guys got real good and melty. Yeah, so the plastic around the lens melted, but the lens itself was fine.
But after making sure all the pieces were there, there's only one thing left to do.
Oh, this is so exciting. Any guesses? Do you think we cooked it?
I think we cooked it.
All right. That is a little cooked. It's a little brown. Let's go! It's a little cooked. All right, you ready? I'm gonna take a bite. Yeah, that's like a good piece of meat. That's not raw. It's kind of, it's a little raw.
Is this the most well-done meat on Earth? No. Is it basically still raw? I mean, honestly, it depends on the lighting.
I'm gonna eat one more piece. Oh, this is kind of gross.
But we cooked it with aerothermal heating. We cooked it by sending a 50-pound rocket to 30,000 feet in the name of science and culinary art.
Here you go, here you go. Yeah! That's delicious!
I couldn't have done this project without my friends, and building something ridiculous is a lot more fun when you're not alone. Plus, nothing brings people together like the promise of meat. And a little gastrointestinal distress. Hypothetically.
Sous chefs, you performed great today. You've made me proud, and I give you 5 big booms. Boom, 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 boom. Can I get a yes, chef? Yes, chef. Okay, let's get out of here.
Thank you to Andrew, Charlie, George, Ben, Max, Zyla, Wes, Elliot, and everyone who helped with this project. BPS is a crowd-funded space program, and if you want to become an intern, there's a link to that in the description below. Thanks as well to the patrons who support this project. For $5 a month, you get access to a behind-the-scenes video every 2 weeks, and thanks to you for watching. My name is Joe Barnard. May your skies be blue, may your winds be low, and may your stakes be high. Goodbye!
This is a rocket plane I built to see how fast it could fly. It uses one of the largest model rocket engines I could get to fly to speeds way faster than any of my previous model aircraft. It's made of cardboard tubes, 3D printed parts, and balsa wood, and is based on the real-life plane that currently holds the record for the fastest plane ever built, the X-15. Over the years, I've been on a journey to build faster and faster RC planes, modifying and upgrading jets to push my airspeed record higher. Currently, that record sits at 145 miles an hour, achieved with a plane I built a couple of years ago. But now, I'm ready to take my model aircraft research to the next level, through designing new planes capable of reaching even greater speeds. And that's why I thought it would be a good idea to build a plane like the X-15, as that plane was NASA's attempt to discover just how fast you could fly, testing new materials and engines to the absolute limit. And that's exactly what I wanted to do with this next plane. The primary objective was to build a rocket plane that could go faster than any aircraft I'd built before. But this wouldn't be easy at all.
Well, that wasn't good.
As going faster makes getting the vehicle back down safely much less likely.
Oh no!
I thought starting with parts from a model rocket kit would be a great idea, as it's almost always simpler to build on something that already exists. I decided on a high-power model rocket kit that came with some really solid components, perfect for building the X-15. The kit included a super strong fuselage tube and some beefy centering rings, which are used for mounting the powerful rocket engine. The only problem was, while these parts were incredibly strong, they were also quite heavy, which could be a bit of a problem. Next, to bring the design to life, I used 3D software to create a digital version of the plane, based on the dimensions of my new rocket parts. And this would be really helpful in helping to make an accurate model of the X-15. Some parts needed to be modified, like the body tube, which was a little too long. Some parts, though, would need to be made entirely from scratch. Unfortunately, the nose cone was one of these items, as the one in the kit didn't match the real X-15. With this, I could just use the CAD model's nose cone, and this was printed out on my Bamboo Labs P1S 3D printer, which only took around an hour. Now we had a nose that exactly matched the real X-15. Next, it was time to turn this rocket into a rocket plane, and that meant adding the wings and tail surfaces. Although this plane was going to start life as a pure, unguided rocket with no control system, the plan was to convert it to RC later if the initial test flights all went well. For now though, the fins and wings would be simple sheets of material with no electronically controlled surfaces to steer it. It would work just like a normal rocket, with a parachute to help it land safely. These wings and tail surfaces were precision laser cut from strong plywood, and epoxied through holes cut at precise locations along the fuselage tube. Since the single sheet wings weren't strong enough on their own, I reinforced them by laminating them with lightweight balsa wood. Now it was all starting to look like a fast rocket plane. The fuselage wasn't just going to be a simple tube though. The real X-15 had distinctive bulges on either side, so I shaped these using strips of balsa wood. This took hours of sanding and filling to get smooth, but after a while it all started to come together.
Right, painting time. We'll start with a mist coat and then we'll build up the layers from there. And I'm not going to put too much paint on because we want to keep this aeroplane as light as possible. It's already going to be very heavy for the wing area. Hopefully it ends up looking just like the real X-15.
With the stickers applied, my Patreon's names added to the bottom surface of the fuselage, and everything fully assembled, our first X-15 prototype was mostly complete, and it looked pretty cool. Of course though, to launch a rocket you need more than just the rocket itself, so we had to prepare all of the launch equipment and rocket motors. This included assembling a suitable launch rail, which would guide the rocket on its first meter off the ground. We would also need a hand controller, which would be wired straight to the electronic igniter.
Whoa!
These are used to set off the rockets remotely at a safe distance.
Ah, there we go.
And of course, we needed to test all of this out to make sure it worked and that we weren't going to have any problems at the launch site. Finally, we turned attention to the all-important parachute, which would allow the rocket to float safely back down to the ground. The second important goal of this project.
hope this parachute is going to be big enough.
On a model rocket, the parachute is usually deployed by a small ejection charge that happens automatically once the rocket has been launched. Once all of the fuel has burnt out, a delay charge ignites, subsequently triggering the ejection charge at just the right moment. This blast pops the nose off the rocket, pulling out the parachute on a shock cord. That's the theory anyway. We'd done multiple simulations on OpenRocket to check that the X-15 would work, but it was looking a little bit narrow on the stability margin.
So that's the centre of gravity. So it's kind of over the wing, which is what you want for an aeroplane. You know, you want it to be over the front 30% of the wing, but for a rocket, you probably want it to be a bit further forward. So we'll see, that could also be a bit of a problem. Based on previous similar rockets I've flown, it's never been an issue. It's just that I'm worried that this one has taken quite a while to design and build, so I don't want it to go wrong.
After a solid couple of weeks of designing, planning and constructing, we could now head up to our normal flying field for the first test flight of our new X-15. The aim for this flight would be to simply find out how well the rocket flew on the smaller F-size engine, which would produce around 6 kilograms of peak lifting force. If it matched our simulations, it should get up to around 108 miles an hour.
I hope that seagull disappears, otherwise it's going to get shot down in a second.
If it could reach this speed successfully, we'd have the green light to fly it on some bigger motors, to try and hit some higher speeds.
We've got this rolling, that's rolling, drone's rolling, all the cameras over there are rolling. Okay, and then we're going to do a countdown? Yep. Okay, so arming, ready, X-15 going for launch in 5, 4, 3, 2, 1, ignition! Oh no! Oh no!
The X-15 had crashed. What had gone so wrong?
Well, that wasn't good. I think our simulations might have warned us about that. Ah, that's so annoying. Right, come on, let's go and look. Oh my goodness! How's that happened?
In one piece?
Oh, it's missing a fin. Oh. It's missing a fin, but it's almost completely unscathed. Parachute came out, so at least that bit worked. The engine successfully fired. It was a bit slow off the launch rail. We actually needed more power, I think, and also more of a stability margin. So yeah, we've got a bit of work to do, and then I think we can maybe try again. This is going to be harder than I thought. Back to the workshop.
Returning to the workshop with a battered and broken X-15, we could start work on studying the footage and figuring out exactly what went wrong. If we could fix the stability problem on the next launch, we should then be able to see a successful flight. Thankfully, our X-15 was repairable, so like all good engineers, we would embark on a thorough program of investigation and improvements. You might have been wondering about where we build all of these rockets and aeroplanes. We recently moved into the brand new Project Air workshop and have been slowly improving it with all sorts of cool features, such as our state-of-the-art model train transportation system to move things from room to room, and have been decorating it with some really cool artwork. These metal posters behind me are from Displate, and they have actually sponsored this video with an ad. Displate.com is home to over 2 million artworks, including license deals from iconic brands and franchises, which can be shipped to you in just 4 to 5 business days, in the form of these high-quality metal posters. Now, the one thing I love about these is the way that they mount to the wall, as it's really quite clever. Basically, you just put this sticky pad onto the wall, which is actually a magnet, and then the metal posters sort of like clunk into place. It's tool-free, and you just use your hands, really, just to press the pads onto the wall. Each Displate comes with a magnet kit, and everything you need is in the box. Also, Displate's latest release, Textra, includes a load of licensed brands, and these posters have premium finishes. Currently, you can get one Displate for 25% off or 2 Displates for 30% off. And this is also available on the Textra Displates. Make sure to check out the link in the description or use the code Project Air. Alright, let's fix the X-15. After reviewing all of the data from the first test launch, we managed to piece together a solid theory about what went wrong. It all came down to the wings. For a stable flight, the CG needs to be ahead of the CP. This ensures that any disturbance creates a restoring torque effect, pulling the rocket back to its original flight path. Fins at the rear of a rocket increase aerodynamic stability by shifting the CP rearward, keeping the rocket steady in flight. The problem with our X-15 is that it's designed like an aeroplane, which has the centre of pressure located over the midpoint of the central wing, where most of the lift is generated. The centre of gravity previously was only a little further forward, meaning our stability margin was very small. Clearly then, we had to make the rocket plane behave more like a rocket. I needed to repair the tail and increase its effectiveness to pull the centre of pressure as far back as possible. At the same time, we needed to make it a bit stronger. I started by experimenting with the original fins from the rocket kit, combining them with balsa wood to create longer and stronger fins. Unfortunately, these turned out to be too heavy.
That is too heavy. I think I'm going to use foam board.
If the fins were too heavy, they would pull the centre of gravity rearward, which would mean we'd have to add even more counterweight to the nose to balance it out. Lightweight fins were absolutely essential.
That's better.
We'd previously tested foam board fins on a rocket plane that reached 145 miles an hour, and surprisingly, they'd actually survived. However, this X-15 would be flying much faster, so I wasn't sure if the foam board would hold up to the extreme airspeeds. However, pushing the envelope and going into the unknown is what this program is all about. With the extended fins sorted, it was time to tackle the opposite end of the aircraft, with the centre of gravity problem. To figure out the right balance, I built a simple stand from foam board. This would help us to find the CG more precisely.
So what we need to do is add lead until it gets to around here-ish. So I'm going to put it on where I want the CG to be, and then I'm going to keep adding lead to this basket until it levels out.
This sheet lead was going to be tricky to get pushed up right into the nose. Helpfully, lead has a relatively low melting point of just 327.5 degrees Celsius, so I could reshape it really quite easily with the help of a blowtorch and lots of protective equipment. Don't try this at home.
First metal cast on Project Air. Looks like we might have succeeded.
After casting the lead into a mould, the result was surprisingly good for a first attempt. Now I had a very nose-heavy nose. One of the final jobs was to install a more optimised camera to capture all of the important onboard footage. So there's the battery and the board and everything in there, and then we've got the flashing light, and that means that the camera is on. Now to prep the new G-size rocket motor, which was twice as powerful as the last engine, and set a delay for the ejection charge. After a final balance test, we were now ready for action. With twice the power and improved aerodynamics, could we now get a successful flight?
So the speed we're hoping to get out of this test flight is 180 miles an hour, which will be faster than any rocket plane I've ever built before. So this will be really useful for when we put our seat on this thing, and yeah, if it can go 180 miles an hour straight up, should have no problem doing that, at least going the other way, or going horizontally, I mean.
As you'd expect, to fly powerful model rockets, you need to follow safety guidelines through ensuring there is enough space in case anything goes wrong with the launch or parachute recovery. So we made sure that our field was plenty big enough for any mishaps. Patiently, we waited for the cloud base to raise and some blue patches of sky to appear as the light started to shine through. I was confident that we'd solved all of the issues, but of course there's always some opportunity for something else to go a bit wrong. If something went wrong now, the X-15 might be completely destroyed and the project would end up in a miserable failure.
Okay, and then we're going to go for launch in 10 seconds.
Whatever happened though, with this higher power engine, it was going to be spectacular.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Three, two, one. Yes! Look at it go! Eject! Eject! Up there! Eject! 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 Oh no. Oh! Oh no! I don't think we're getting that camera footage back.
That hit with force. Oh my.
Oh no! Did you hear that scream?
Yeah! Oh my.
So the rocket was down in the field, but not exactly in the way that we intended.
I think it's actually just stuck in the ground.
In one piece.
I think that's what you call a lawn dart in the the trade. Oh no! I think I can see what happened. Well, I can see what the result is anyway. I don't know what happened.
Thankfully, we had of course taken precautions for this eventuality by flying in a field big enough for this sort of crash landing to occur as safely as possible.
Oh, it's a proper lawn dart, that. I thought the rest of it was just going to sort of explode everywhere. The only bit that's come off is part of this side bulge and this sticker.
Due to the soft mud, amazingly, the airframe was almost completely intact, which was quite a surprise.
It's like a golf hole. We just made our own golfing green.
The rocket had successfully stayed intact on its journey up to 800 feet, enduring an incredible 9 Gs of force on launch without showing any signs of stress on that balsa wood and foam airframe. But something had gone very wrong with the parachute system. After some investigation, I figured out that human error with setting up the rocket engine was to blame. Unfortunately, I'd left too much of a delay on the delay charge, and what had happened is I'd got the timing wrong. Instead of deploying mid-air, the delay charge actually ignited only after the rocket had actually hit the ground. It was frustrating not to get the plane back in one piece, but what a spectacular flight it had been. The rocket plane had proved its durability in high-speed flight and given us valuable knowledge to go forward with for the next aircraft. I'm so pleased that we got this thing to 180 miles an hour. Now, although the original plan with this was to turn it into an RC plane, I don't think that this is the right aircraft to do that with, because it's turned out to be so heavy and have such a small wing area that, yeah, I think we need to go a different direction with that. The direction I do want to take this X-15 program in, though, is to just keep it purely rocket themed and just, yeah, increase the size, increase the power, and see how fast we can get a rocket plane to fly on high power engines. Can we even get close to the sound barrier? That would be amazing. We're going to be doing loads of aircraft videos this year, so make sure to hit the subscribe button down below if you haven't already, and also watch this video next so that you can, yeah, watch more Project Hair stuff on YouTube in the meantime. And if you enjoyed this video, you'll probably enjoy this one too. So yeah, subscribe, click on this video, and I'll see you on the next one.